Hello, everyone. My name is Trey Skillantine. This presentation is my literature review project for CST 5320 on string matching algorithms. Today, I'll walk you through how string matching develops over time, some of the most influential papers, and why this problem continues to be the central to computer science. String matching is not just about text. It plays a role in search engines, DNA sequencing, and even cybersecurity. It is one of those problems that looks simple on the surface, but gets very complex and important when we deal with massive databases and real world application. All right, the big idea. The big idea behind string matching is straightforward. We want to find patterns inside larger bodies of text. That can mean finding a keyword in a search engine, detecting malware in real time, or identifying a DNA sequence. The challenge comes from scale. Text can be billions of characters long, and naive methods that check every position become far too slow. What researchers discovered over time is that the key is avoiding wasted work, finding ways to skip ahead, processing information, or use clever shortcuts that still guarantee correctness. Efficiency is everything in this field, and that's why the problem is still relevant after many decades. KPM started in 1977. One of the earliest breakthroughs was the Kenneth Mortis Pratt algorithm, or KMP, introduced in 1977. Before KMP, naive method simply checked every possible starting position, which meant rechecking the same character over and over again. KMP solved this by introducing pre-processing steps that build a failure table. This table tells the algorithm how far it can safely skip ahead. Whenever a mismatch occurs, as a result, KMP guarantees linear time, which was groundbreaking at the time, which makes KMP memorable. It is not just the math, it is elegance of skipping over repeated work. And the set foundation for efficiency and pattern matching and influence nearly every algorithm that followed. All right, the hybrid approach. In 2008, Musser and Kishnevov introduced a hybrid approach that combined the strengths of KMP and Boy-Moore. Boy-Moore is another classic algorithm that skips ahead based on mismatched characters and often runs faster in practice. The hybrid algorithm adapts to the data. When working with small alphabets, it behaves like KMP. When working with large alphabets, it acts more like Boy-Moore. This means it guarantees good worst-case performance, but also achieves faster average performance in many cases. The algorithm was implemented into C++, standard template library, which means it isn't just a theory paper. It actually shapes how programmers search sequences in real-world code. This bridging of theory and practice is why the paper stands out. All right, reversible computing. By 2022, researchers were exploring how classical algorithms could be adapted for new computing paradigms. Gluck and Yokima published a paper on reversible computing, where every step of the algorithm can be undone. This is especially important in areas like quantum computing and energy efficient computing. where wasted computing means wasted energy or lost quantum states. That they demonstrated that even basic algorithms like Rabin-Karp and naive approach could be rewritten in a reversible way without increasing their time complexity. This research shows how problems like string matching remains relevant even in cutting-edge areas like quantum technology. It opens the door to asking what other classic algorithms can be made reversible and how might the impact the future of computing. Indeterminate strings. Another challenge researchers tackled is dealing with uncertainty in data. Dahini, Maskar, and Sif in 2022 focus on determining strings where some positions are unknown or can be represented by multiple or possible characters. This happens only often in biology, like when DNA sequences include wildcard bases or in noisy databases where errors exist. They extend KMP and Boy-Moore to handle these cases, creating what they call KMP indent and BM indent. These modified algorithms could easily search even when uncertainty is built into the data. They tested them on real-world DNA databases and set them BM indent often outperformed KMP in practice. This work highlights how algorithms evolve to stay useful when the problems themselves change in nature. Parallel algorithms. A database grew larger. Think about the entire genome or massive social media archives. Speed became a bottleneck. In 2021, Hong and Yoon worked on a parallelizing Rabin and Karp algorithm. Rabin and Karp is particularly good at searching for multiple patterns, but it can get slow on very large texts. By using Haskell and multi-core processors, they were able to split the workload and process selection of the text in parallel. They tested this on human genomes and saw significant speed improvements. This work showed that string matching can benefit from modern hardware advancements. Looking forward, parallel string machine on GPU or distributed systems could make these algorithms even faster, opening new doors in information and big data analysis. Synthesis. When we back and look at all of these works together, a clear theme emerges. String matching algorithms have continually adapted to new challenges and environments. KMP sets the foundation for efficiency in the 1970s. The hybrid KMP Boy-Moore work showed how to balance theory with practice. Reversible computing linked the field to emerging paradigms like quantum computing. The indeterminate string work demonstrated how classical algorithms can handle uncertainty in biological and noisy data. And parallel approaches showed that with modern hardware, even massive data sets like genomes are within reach. The trend is clear. These algorithms are timeless, but also flexible, always evolving with the needs of computing. Looking into the future, we can expect even more integration with hardware and in AI. GPUs are distributed systems will allow algorithms to process data sets that are far beyond their capacity of a single machine. Artificial intelligence may also play a role in guiding and accelerating searches by predicting likely matches before the algorithm even finishes. As the data continues to grow, especially in areas like geometrics, cybersecurity, and natural language processing, string matching will remain a fundamental problem that drives innovation. It's not just a theoretical computer science problem, it's an applied one that affects technology in many industries. In conclusion, string matching is one of those rare problems in computer science that is both deeply theoretical and incredibly practical. From its origins in 1970, the algorithm like KMP, to modern adaptations for quantum computing, DNA sequencing, and parallel processing, it has remained a vital area of research. The fact that researchers are still publishing innovative papers on string matching today show just how central it is. It's a problem that connects the past to the present and the future of computer science, and one that will likely continue to inspire new solutions as our data and computing environment grow with more complexity. All right, we have time for a few questions. Um, we're going to go with some that I've already prepared. What's the main difference between KMP and Boy-Moore? KMP guarantees linear time in the worst case by processing the pattern and skipping unnecessary checks. Boy-Moore is faster on average because it skips more aggressively using mismatch rules, but in the worst case, it can degrade. That's why hybrid algorithms combine both strengths. All right, I guess we'll do another question. Why does reversible computing matter for string matching? Reversible algorithms are important in quantum computing and energy efficiency. In reversible commuting, no information is lost, which means less wasted energy. While this isn't critical in the classical computers, it is essential for quantum systems. I guess we'll do another one. How does string matching apply in cybersecurity? String matching is used in intrusive detection systems and malware scanners. For example, scanning network packets for attacks signatures relies on fast matching. The quicker the algorithm, the faster the threat can be solved. All right. Which algorithm would you personally extend if you were doing further research? That's a great question. I would extend the parallel Rabin-Karp approach by testing it on GPUs and distributed clusters. Scaling is the biggest challenge with today's massive data sets, and GPU-based or distributed string matching could process billions of characters much faster. Is there a best algorithm for all situations? No, not a single algorithm is the best case for every case. KMP is reliable for guaranteed performance. Boy-Moore excels with large alphabets. Rabin-Karp is strong for multiple patterns and indeterminate variance and critical in biometrics. The right algorithm depends on the data and the problem context.